Cool, clap. He is the engineering manager at Twitter, and he started and founded how do you pronounce it?
Locomatics.
Locomatics in Sunnyvale, and which was acquired by Twitter. He is also on the faculty of the EECS department at UC Berkeley. Fun fact, I am a EECS student at UC Berkeley, so yeah. He's also the author of a best-selling book called Network Routing, and that has had several publications, and he's also the owner of 10 different patents in data processing. Wow. And from Madurai. He will be sharing his experience and expertise in big data analytics and stream processing.
Thank you. Okay, so this is a little bit of deep tech, I guess. I'll try to simplify as much as I can, but if something goes beyond understanding, either put up your hand and say, hey, I don't understand what the heck is going on, or we can talk later after the talk is done, okay? Anyway, so I manage the real-time team at Twitter, and so that encompasses a bunch of infrastructure technologies that enable real-time. As you all know, Twitter is considered as a real-time information dissemination network. And so because of the true real-time nature of it, our infrastructure has to be designed with the various trade-offs to kind of support that model. So towards that end, my team developed the new technology called Twitter Heron, and it has been operational at Twitter for nearly 2.5 to 3 years now. And this is probably one of the fastest projects that we ever executed at Twitter, and start to finish 9 months before it went to production, because of the extreme critical nature of it. So I'll be talking about that a little bit. So any other questions before I start? Oh, okay. So my background is essentially like I currently at Twitter, and also teach at Berkeley, because teaching is kind of a fun activity that I do. And one of my friend up in Berkeley, he's a faculty called Joe Ellerstein, and he told me, hey, come and teach that course. I said, oh, I'll be happy to do it. It's because teaching also gives you good information about what students really want to do right now. And that also it allows you to impart all the knowledge that you have learned to the students and the youth that who might be interested in learning more about those data areas. And before that, I was the chief product officer of a company that we founded called Locomatics, where we were doing what we call spatial streaming. I don't know how many of you have heard about spatial streaming. The idea was if the data is if the GPS is going to be embedded everywhere, the data generated out of those is going to become a huge deluge. And so how do you process that data and write cool applications on top of it? So for example, one simple example is, hey, by the way, I need to put a reminder when I am close to the dry cleaner, I need to pick it up. So you can get a reminder, boom, like when you're close to that area of within a mile radius or probably half a mile radius or whatever, right? So those kind of cool applications that you can write on top of it. So we sold it to Twitter, and then that technology is essentially become Twitter Heron in some form. And because of that, there's a lot of public interest on this technology, because the technology is open sourced and anybody can use it. So because Twitter is very open source friendly, any technology that we implement, except the core critical for business, we open source it because we are a big proponent and believer in open source, and kind of enable the community so that we can all collaboratively work together. So that is then before Locomatics, I was at Juniper Networks, and where I was working in a lot of kernels, protocols, and a bunch of technologies. And before that, I was in a startup. Then before doing the startup, I finished my PhD at the University of Wisconsin-Madison, where I was working on big data. I mean, big data at that time, nobody heard about it. We called it in an MPP system, but everybody now calls it a big data now. So it's kind of what we call as the computer science comes back every 20, 30 years. The same ideas get repeated itself in some fashion. So that's what we are seeing right now. So anyway, that is my some short background. So let me go ahead and carry on talk because I have a few slides to cover. So I'll be talking about Morley Heron. Um, Okay, so the talk outline will go as first I'll give you an overview of what the whole space of analytics, because typically everybody talks about big data analytics and all, but what is it? So just to give you a high level overview and where does the real time fit into that big picture. And then I will go into details about what Heron means and some of the cool things that we did with Heron from a technology point of view. I'll go into that. And finally, I'll conclude it with some use cases which we think, but primarily the use cases are with respect to Twitter, but it has a lot of applicability in other domains and other industries as well. So what is analytics? There are two different components to analytics, and the first is discovery. I mean, the ability to identify patterns in data, whether the data is small or big or medium, whatever might be the case. Now, once you discover some patterns into the data, then you got to communicate it. So how do you make that data make useful for you in some fashion, right? So typically, if you look at enterprises, they are on two missions. One is to increase the sales and increase the bottom line. The next one is to save costs, again, which increases the bottom line. So you have to provide this in a meaningful way so that the patterns that you have discovered is useful, because you're going to be costing some amount of money in order to even discover those patterns because of all the big data technology, infrastructure investment, and all the personnel that will go along with it. So there are multiple different type of analytics, and one is cube analytics. So how many of you know about cubes? Or the other term is called business intelligence. So cube is more on the side of the technical term for the business intelligence, but if you look at it, the evolution of the cube, it started in the late 90s, and then it kind of evolved into a critical tool for everybody to slice and dice the data, which are represented in a multidimensional data form. So for example, how much my product sold in a particular region between this time. So you can think about time, product, and region as dimensions of a cube, and you can slice and dice a cube. I mean, of course, it doesn't restrict to yourself to 3 dimensions. It can go to n dimensions. So that is one of the big analytics that is in play. Now, the recent trends, I mean, last decade or so, predictive analytics have come into play. One is the statistical-based analysis, where you use statistical methods like a linear regression and clustering and associations and all those other aspects to mine the data to identify patterns, rather than looking for a particular pattern. What are the patterns that emerge out of it? So that is what more of a predictive analytics. Now, these two broad categories of analytics can be done in different dimensions, and one is called streaming. So essentially, streaming is the ability to analyze the data immediately the instant it is produced, in the sense once the data is produced from a data source, and that data source could be a variety of data sources, and it is put through some kind of a processing pipeline, and the data is processed immediately right away. And this is also like people generally call with another variant of the name called data in motion. So that is a broader category. And the next one is what we call as interactive. And the interactive, what happens is the data reaches some kind of a storage, or data comes to a rest. The data is not moving anywhere, and all data has come to a rest. And then you're querying the data. And the difference between streaming and interactive is, even though they are real time, the interactive allows you to query the data at rest, while streaming is doing the data in motion. And in interactive, the budget for time is to come, and the results has to come back within a few seconds, so that you can do an exploratory, like for example, hey, I wanted to see what here is going on. Oh, I got some results. Now I wanted to further drill down onto that, whatever the results it gave. So you can be more of an ad hoc exploratory kind of analysis of data. And the third category is the batch, which is essentially like looks at a lot of data. I mean, probably hundreds and petabytes of data, where it takes a long time for the results to come back. I mean, I have seen jobs that can run for even a day or even a week, because of the fact that it's looking at a lot of data. And that is the third category. And most of the time, these batch data is batch analytics is geared towards more machine learning or trying to compute like yearly worth or multi-year worth kind of data, right? So then, since the focus of my talk will be on the streaming aspect of it, there are two shades to the streaming itself. So one is called stream processing, and that essentially acts on the data in motion and using something called continuous queries. Don't worry about the term continuous queries, but essentially what it happens is like you go a query to the system, and the system is constantly evaluating the data against that query on and on as the data is continuously coming through. And so when some action has to be happening, take an example of an apartment building where you have a lot of sensors in that building for every apartment, and if the smoke detector detects something, then you wanted to call a 911. And so the data that is constantly being monitored is the sensor data, and some processing element will be kept in the apartment or in the cloud somewhere where the data is continuously ingested. And then the query, when the threshold of the temperature data that you're measuring goes beyond like 80 degrees, then you kind of, call 911. And even then you can attach some conditions like it has to be sustained for like 10 minutes or 20 minutes or whatever it is, right? So that is what we call as a stream processing. Now, then another broad is called streaming analytics. I mean, how many of you have used Twitter app? Okay, so how many of you know hashtag trends? Right, so those are all nothing but streaming analytics. So where the new data that is coming in is constantly computed against some kind of the top trends based on hashtags or whatever, and the top 10 is always bubbled up, or top 20 is always bubbled up. That comes at the hashtag, served as a hashtag to all the consumers. So that is an example of real streaming analytics. But there is another example is like where we have some kind of command center where we can monitor where the tweets are coming from at any given time, and whether there is a spike in certain region or certain operating devices that people use, right? So these are some of the insights that we always continuously get it, because being a real-time network, we wanted to kind of know what's happening all over the world. If it comes in, because as you all know, the news breaks out to Twitter much earlier than even the news folks pick it up, because it has that much of real-timeness into it. And because of this real-timeness, we just keep monitoring those to look for those appropriate items that get our attention. So then, as I said, the difference between the streaming analytics from a system level is where in interactive analytics, where you have the data is loaded into the database server, not continuously, once in a while, and after that it goes into storage, and you keep running queries on top of the data that is existing. So that is more of an interactive analytics. In the streaming, that's the paradigm is inverted, where data is continuously going. I mean, here the query is being continuously given to you. Here the data is continuously going, the queries are programmed. So which means these queries are not changing often. Instead, the queries are evaluated against the data. So that is a key difference in streaming versus interactive. And so some of the streaming system requirements include you need to process massive amount of streaming events. I mean, of course, within the context of Twitter, we get lots and lots of data. In fact, like the Twitter data that our people see is a small amount of whatever we do, like probably around 3 to 4% of the data. But the data that we collect for analytics is probably worth 95% of the data. So then you have to, of course, you have to do a lot of performance and scalability as the data volume increases, because our data keeps increasing like at around 30 to 40% every year, and that's a huge amount of increase. And of course, we need to make sure that we can get real-time responsiveness to changing conditions. And of course, we have to, since a lot of data sources are there within Twitter and even outside, we need to make sure that we integrate with those data sources. And this also needs a new paradigm of visualization, because of the fact that data is continuously pushed and the results are continuously pushed. The visualizations have to be, rather than doing a pull-based visualization all the time, this data is coming at you, then the visualization has to react to it rather than doing a pull-based visualization. So then sometimes the budget, like how much time do we get in order to process this? I mean, how many of you heard about OLTP systems, which are kind of standard systems? So those systems operate under the 500 millisecond latency sensitive budget. On the other hand, if the batch is kind of approximately an hour or so, and that is used for computing or looking at a lot of data, and on the other hand, real time sits somewhere in the middle, it should be less than 2 to 3 seconds, and it depends on the application that you want to go into. Like could in our budget, it might be like as high as 2 seconds, but there's a gamut of application that wants probably in less than 10 milliseconds too. So like I would say that budget is from 10 milliseconds to all the way to 2 to 3 seconds is where the real time sits in actually. And I mean, if you look at, as I said, it's a vertical based from a timing perspective. Because if you go to Wall Street folks, then ask real time means, oh, give me nanoseconds or picoseconds, because anything that they gain advantage to get a trade executed earlier than you, so it translates into millions of dollars for them. On the other hand, if you go to retail folks, what is real time? Oh yeah, it's 12 hours. So it varies depending upon what the customer wants and everything. So then, if you look at a streaming data flow, it's essentially like a data flow through a DAG. I don't know how much of you, this is a little bit into computer science principles, but the DAG is nothing but a graph actually. So where the arrows represents the data that is flowing through, and the individual circles represents where the actual processing is happening on the data. The data goes in, process it, and the data goes out. And so that way it can be structured as multiple stages, and every stage does its own thing, whatever it has to do. And so that is a high-level concept. And of course, the streaming, I don't want to go too much detail into it. So here, the streaming systems, what happens is when the data is given to it, it will try to do the best effort in the conditions, whatever it prevails, to make sure the data gets through processing. And there's a chance that data might be dropped also in the middle because of the failures and all the various things that can occur. So that's what are the best effort processing is called at most once. And at least once is it guarantees that even if the data gets dropped or not processed, it makes sure it's replayed back so that it guarantees that all the data is processed always. So that's called at least once. But the drawback is that it's possible that the same data could be processed more than once. And the exactly once is tries to do the correct thing where it will be guaranteed that it's executed only once, right? The data that is entering into the system is made sure executed only once, not more than once, and not even failed also. So that is the three different semantics. And one of the things in streaming systems that always you encounter is called windowing support. And especially like since the data is continuously coming at you, I wanted to say, hey, I wanted to look at the last 10 minutes worth of data or last 100 data items that I have been receiving so far, right? So that is what we typically call windowing. So if you look at it like the input events, so here the window size is determined by how much time that you want to, like last 10 minutes or last 20 minutes, and what are the events that come within that window, right? Then if you can even express some kind of computation on top of each window. So in this case, I'm just doing a sum on top of that window. So which means like within this window, 3 plus 1, that the sum is 4. Here, there's only one event, which is 2. But here in this window, 7 and 5, which gives to 12, right? So that is the notion of window, and which is a fundamental concept in streaming systems. And so there are a couple of windows. One is called sliding window, so where if you specify a sliding window of the last 10 minutes at a 1 minute granularity, then every minute that window is moving. So think about the last 10 minutes, it keeps moving at every minute. On the other hand, tumbling window essentially finishes up the 10-minute window, whatever you are on, then resets the window, then they wait for the next 10 minutes. So that is called tumbling windows. So these both are commonly used in streaming systems. So there are a bunch of streaming systems that have been in play for a long time, because the streaming is not a new technology if you look at the whole history of databases and all the big data processing elements. So this is in the early 2000s, there was a second generation of streaming systems that came into play, and that is all like came out of universities. I mean, so I was personally involved in the Niagara query engine, which came out of Wisconsin-Madison. Then Stanford, of course, had their own Stanford Stream Data Manager, and MIT had this Aurora Stream Processing engines. Then they have followed up with another project called, which is distributed. Then finally, Cornell had something called Cayuga, which is a stateful event monitoring systems. But But these all these second generations were driven by how to express all the streaming in the SQL, because SQL is a universal language which everybody knows, and can we turn that language into a stream-based, to do stream-based applications, right? And that seemed to be worked very well, actually. So some of the, what do you call it, the companies that get born out of these projects were kind of acquired by several companies, I think, because I think the Aurora became a stream-based, and the stream-based was acquired by TIPCO, and I think the Stanford Stream Manager became Correlate, and that was acquired by a Swedish company or whatever. Then in the third generation, which is the generation that we are right now in, we have a bunch of systems like the S4, that is one of the initial system, came from Yahoo, and the Twitter open sourced something called Storm like 6 years ago, and Samza was open sourced by LinkedIn. Then Spark, of course, everybody knows it has some streaming component along with it. Then this is our new system, which is a next generation system called Heron, actually. So there is two different type of fundamental things how you implement the streaming, and one is called native streaming. So where the data comes in, and the moment it comes in, it's processed right away. So that is called event processing, essentially. So in other words, like events process immediately as they arrive. So let us say, like, if this is the guy who's getting the data, immediately it puts into whatever it has to do and sends the data to either a select or a project or whatever might be the case. And similarly, like if this guy has to get the same data, it will also do something immediately and send that out. So even one data coming at a time and at different intervals, immediately they will process. So the advantages is low latency. You can achieve a lot of low latency because you can even go down to a budget of 10 milliseconds because it's immediately processed. On the other hand, there is something called micro-batching, where you get the data, then after that you chunk the data into some batches. Like, okay, I wanted 100 tuples per batch or something like that, right? So then you give that batch to the source operator, and they will do a simple map reduce on that batch and get the results out. And so the one advantage is like of this one is like it can have a high throughput. So which means it can process a lots of data, but the latency will be pretty high on these cases. And fault tolerance is easier to do because of the batch nature of it. So now, so this was just an introduction to the kind of the area. I mean, do you have any questions before I go further? Yes.
So for the form that you talked about, 10 milliseconds to 20 seconds, right?
Mm-hmm.
What is the compute engine that you would need behind the screen to be able to meet that level of?
So the compute engine is what do you call, like, I mean, we do commodity processors only. Okay, so I think like we feel processors are much faster now, but the most of the time goes in how fast we can move the data around over the network and all the various things. That's where the time goes, actually. So it's not the computation that takes a bunch of time, but computation could take time, and you cannot move the data depending upon the algorithms that you do in real time. For example, if you are doing some heavy machine learning kind of an approach or algorithms, then the cost of doing those machine learning or the statistical methods and all the various things that you compute will take much more time than the speed at which you can move the data. So those are the kind of things you can pick up. Okay? Yes?
You mentioned about windowing.
Uh-huh.
So windowing is happening in the real time.
Yes.
The question is, suppose we wanted to authenticate something in 10 seconds.
Mm-hmm.
Where the 10 seconds data is to be processed? Will it be in memory or in
That depends again, like it depends on the size of the window.
Karthik, can you repeat the question, please?
The question is like when you have a window of 10 seconds, where is the data is maintained? So the data could be maintained in memory or partially in memory or disk, or so that those are the two approaches, predominant approaches. And if the window size is small enough, it makes sense to fit that in memory so that you can do fast lookups and fast computations, right? And when window becomes larger, beyond the memory size, then you just need to spill over to disk or even flash. And so at the time, some out-of-core algorithms that you have to do to minimize the number of times you have to read out of the disk, because disk will become bottleneck at that point.
Yeah, another follow-up question. Since the incoming message is going to be, is there any limit on what should be the optimal message that streaming can do efficiently? Is there any
No, like that is a question of provisioning. So like if I give more resources, yes, I can handle any amount of data, right? So I have jobs that run like on a couple of machines to all the way to 800, 900 machines, because the sheer size of the data that you have to handle or process is so high that we need to make sure the appropriate resources are given. So once the appropriate resources are given, it takes care of, it can handle that. But the thing is, the more the resources that you give for a job, the more and more distributed systems, all the concepts will come into play. And we have to make sure that fault tolerance and all the various things, and we don't want any manual intervention when some failure occurs. Automatically, it has to be designed so that the failover is managed or self-healing. That's what we call it, right? So to take care of those things. Okay. So the here and I will just go a little bit faster because I don't want to go too deep into it. But as I said, like any streaming is going to be a DAG, and DAG is called nothing but a topology, and there are two types of elements in a DAG. It's called a spout, which is essentially inject the data into the topology, and the bowls, which essentially does the processing elements. And to give an example of how it looks like, essentially looks like a DAG. So where you have two spouts, which in turn taps the data into a data sources and gets the data and injects into a topology. And this is essentially the bowls which are getting the data and processing the tuples that are